category of proximity because it does not make any physical contact with what it's trying to measure. So, of course, these things are sealed up. What we have here is we have some that's not sealed up. Here's your magnet reed switches. So this is a really good picture right here. So we have two types. We have what we call dry contact and mercury. You don't see mercury much anymore. You might run into these, and why? You don't see mercury. You don't see mercury switches. You don't see mercury switches. Yeah, mercury is very dangerous. But if you get into an old application, you might see this. This is an old thermostat. And this is glass, guys, so don't drop it. But this has a mercury switch in it. So it used to be an OHVA system thermostat. And if you got a real old house, you might run that. But while we're looking at it, when you look at that glass, you see there's a contact inside there. And there's an open space in there right now. Can y'all see it? Of course, this would do better if I use this to light a light, but what this thing does is that we have a magnet. So what these guys do, they sense a magnetic field is what they're doing. Oops. Okay. So here's our reed switch. And right here, this is the actual switch itself. Now what this thing does, if it comes up in with a magnetic field, a north-south field, then what it does is the switch itself will close. So what I'm going to do is I'm going to get my meter and put it on a continuity check. And I just dropped my reed switch. Of course, I got some more up here. So we got it on continuity. In electronics or electricity, when we use the term continuity, we mean the resistance between 2 points is less than 1 ohm, right? And so what these guys here do, we use this so often, like tracing wires and stuff like that. So instead of coming up and having to look at our meter all the time, if we do this, we know we have continuity or little or no opposition. If we do like this, we know we got an open, right? So all I'm going to do is I'm going to take this and put it across my switch. Oops, let me try to anyway. Of course, it's not going to work. I might need a different type of magnet. This is not, probably not stronger. It don't take much. It's just you got to orient it so the field travels through both the switches. And this doesn't seem to be doing the job. It shouldn't take that much. Normally these things don't use expensive magnets. They use just bigger old. Of course, the best laid plans, right? Oh. These things can be very, very small. The ones we have are extremely small. Either that or I wouldn't put them in there right. So what happens is the magnetic field, so you don't put a north pole, you don't put a south pole, you got to have a north-south pole. And it just comes in there when it comes in the, let me get it over. This guy's really sensitive. So what's making that thing is when it flows through there, north south, and what does north south do? They attract each other, right? So this is a really, really good example right here. So this is what I'm doing, and I'm putting this across the north-south. So you're not putting north, and you're not putting south. You put it across the magnet long ways, right? You understand that? And when it does that, what happens? Well, the contacts close. So to do this, we got to have a magnetic field. What's the disadvantages of a reed switch? Huh? Yeah, it's mechanical. So that means we've got contacts in there. Now the contacts are in a vacuum, so they don't arc, but we still have a contact in there. It's mechanical moving parts. So these guys, if they're going to fail, they usually fail mechanically. But they're not designed to handle a lot of current. They're designed to just give us a signal, right? These things are used predominantly in burglar alarm systems. The sensors that you put on your doors and the sensors that you put on your windows. Well, what you do is you put a little magnet unit on the window, screw it in, and then you put the reed switch on the other side. And if somebody opens your windows, it signals the alarm that somebody's opened your windows, right? So these are used a lot. We use them a lot in industry, especially since they've done something pretty neat in that they started on our pneumatic cylinders. We use these so much. If we got it, first of all, the cylinder itself has got to be plastic, or normally it's aluminum. And what they actually do is they put a magnet inside the actual right next door. They put a magnet on the actual piston itself. And then what we can do, aluminum will not concentrate magnetic field, so the magnetic field can come out. And what we can do is we can strap what? We can strap Hall effect sensors on this thing, not Hall effect. We can strap what? Reed switches on this thing and actually know when the cylinder's what? Extended, or we know when the cylinder's retracted. And we do this a lot now. This is very, very common to be able to buy these magnetic fluid, these fluid power cylinders that have the magnets on the actual rod itself. Are we okay? Pretty high. So normally we like to. We're a visual species, so we like to see things made up. So what they'll do is they'll come up here and we'll have our reed switch. And what they'll do is they'll just put an LED in series with it. So what happens is what? When the reed switch is made, it lights up, and when it's not made, it don't light up. So this is very, very common on these magnetic reed switches too. So we got a visual indication if the reed switch is made or not made, and we don't have to do what? We don't have to get our own meter out. Okay. So all the reed switches that we have, photoelectric sensors. Detect the presence of an object using a light source. These guys here normally have digital outputs. These are solid state. That means they're going to have at least 3 wires going to them, right? Power, common, and then a signal wire. Okay. That's a standard color code too. Pros, they're solid state, no moving parts. Cons, they require a clean environment. Some of the guys says they have to go out there and make sure these things are clean because they work off lighting. Lighting don't like to be blocked, right? When it's not supposed to be. Requires a power source to operate, and these guys here will drop a voltage because they're solid state. They're not a switch. They use a transistor, and we'll talk a little bit about that. We have 2 types of transistors. One's called a PNP and one's called a NPN. Normally, this is a transistor switch. So it's not actually a mechanical switch. It's an electronic switch. And these guys here will never drop 0 low. So a normal contact, when it's closed, it's good. It's going to drop a voltage that we can't even read, right? You understand that with our meters. These guys here are going to drop a voltage, and they'll show you how much voltage they'll drop. Which becomes very important for these things in series. Basically, mechanical contacts, you can do more in series. Solid state and solid state switches, you're going to be limited to the number that you can hook in series. If they drop 2 volts apiece and you're running off a 12-volt supply, you run out of voltage real fast to operate the rest of your circuit. So that's one of the other things. So what kinds do we have? We have 3 basic categories. So photoelectric sensors, and we'll go back. We got tons of these on the Festo land. And so here they are, and you're about to know this. We have what we call a diffuse reflective. So what a diffuse does is it actually bounces light off the object that it's trying to detect. So just about everything returns light, right? And in fact, that's the way we get color. That's what we're seeing. People don't understand that. But the shirt is not green; it's reflecting what? Green, and that's what your eyes pick up. So you're looking at reflected light. Of course, this guy has problems with black colors, right? You understand? So black reflects. Of course, what we have to understand is there's really no such thing as pure black. So even black reflects some color. So, the problem with the diffuse sensor is that the distance. So if the light is red, then a red will reflect a lot of light. So that means red could be further away, right? You understand? But you come in and you get a real dark color, then what happens? It's going to have to be a lot closer to be able to detect it. So that's the problem we have with diffuse, is that we get different amount of reflection depending on the color of the object that it's bouncing off of. That makes sense? But if we're doing the same color, we could set the sensitivity on that thing and we could make it do what we wanted it to do. Then we have what we call a retroreflective. These guys are real good. So what we do is we have a retroreflector. A retroreflector is basically a reflective surface that's made of 1,000 low triangles. And what's nice about a retroreflector is that it will return light back to the source even if it's at an angle. So that means your retroreflector does not have to be perfectly aligned. And you see this all the time. That's what people wear at night when they're on, You see some people on motorcycles that wear them. Some people ride bicycles that wear them, because you don't have to be lined up perfectly. If it was a mirror, the angle of incident is going to be equal to the angle of reflection. So if you're off to the side and it's a mirror and you're at this, it's going to reflect off somewhere else, right? You understand? So retroreflectors over a viewable angle, it's not infinite. And you see that when you see a retroreflector, the closer you get to it, sooner or later it just disappears, right? You understand? Huh? Yeah. So retroreflectors. So these are pretty neat. These only have problems with transparent. So we wouldn't use a retroreflector to detect clear glass, right? You understand? But just about everything else, we're going to get some right and light. We set the sensitivity on that. Then we have what we call a through the beam. Through the beam, the big advantage of through the beam. So think about it. If my light, before it disperses too big, if it can travel 6 feet, well, that means a retroreflector would have to be within 3 feet, right? Because why? 3 feet out and 3 feet back. Through the beam, if you've got a light source that can give you a nice beam over 6 feet, then by George, you can put the receiver, 6 feet away. So through the beam has the ability to have the greatest sensing distance as far as how far the object is away. So these are the 3 primary light sensors that we have available, photoelectric sensors that we have available. Okay, what we're going to do now? And let the instructor live that down. Through the beam. Are you okay there? Any problem? Retroreflective. Are we okay there? If you're in the sensors class, this is one of the ones that you'll actually wire up. And then the diffused. Everybody okay there? We have what we call a through the beam, but it's made special, and in fact, it's referred to as an optical interrupter. But it is nothing but a through the beam. It's just that your transmitter and your receiver are permanently mounted inside this little unit, right? Very common a lot of places. And where we have this on, we don't have these on the Amtro line. We do have, we don't have them on the Festo line, but they're on the Amtro line. Very common on printers, very common on open loop systems like stepping motors, where you're trying to find where something is one time, and then after that you keep up with it by knowing where it started from, right? So these guys are very common on dot metric printers, where when you turn power on it, and you hear it finding itself. You come over, and that's probably what it's looking for. It's looking for one of these optical interrupters. So it'll have a plastic blade down there somewhere on the print head, and it goes over there and hits that interrupter, and now it knows where zero's at. And then from then on, it knows exactly where it's at. But these are optical interrupters. Next time we go back to the line, we'll go ahead and look at those. We won't go back there now because these are nothing but Hall effect. Hall effect is another device that senses magnetic fields. And I'll have to go over there. But these guys have absolutely no moving parts. These are solid state. They sense it electronically. Senses the strength of the field. So we can use this guy right here to sense the strength of a field. We can get the analog type, or we can get what we call the latching type. The latching type basically looks for two things. It looks for like a north, it calls it to latch, and then it looks for a south, to call it to unlatch. We've got those. We've got some analogs, but they just came in. Of course, an analog device, most of ours are analog devices, but they go to an A to D converter inside the sensor. And so that means we'll have a lot of adjustment on it. We'll have a little sensitivity, so it gives us a digital output. A digital Hall effect has the A to D built inside it. It's a little old tiny thing too. These things are very, very small. So what advantage does it have over a magnetic reed switch? No moving parts. Disadvantage, of course, these guys are going to have 3 wires going to them. What's the 3 wires? Power, signal. Power, 2 for power, 1 for your signal. They share the common, so that the signal and the power share the common. These guys here don't sense metal, they sense what? Magnetic fields. And we'll have to look at those and figure out which one they are. You can't tell them. They look a lot like a Hall effect. They look a lot like the magnetic reed switches, but there are some Hall effects on there. How can I tell the difference? Well, when I look at the schematics, they'll have 3 wires going to them, and a reed switch will only have what? 2. This shows you basically how they work. By the way, Hall effect, we have a problem. We have a type of, it's not a current meter. We call them clamp-on ammeters. Have y'all heard of those? Now, clamp-on ammeters, the amount of current, the current to a conductor. So every time you put the current to a conductor, it sets up a magnetic field around it, right? You don't understand that. The strength of the field is directly proportional to the amount of current that flows through that conductor. Now, we have the ability to induce voltage into another conductor. We call it mutual induction. And what determines if I'm going to take one conductor with a magnetic field and induce a EMF or induce a voltage into a conductor beside it? Anybody know? I don't know. I didn't think I started up Skype. Where's my PowerPoint? Okay. No. There we go. This is a PowerPoint. It's not the right one, but it's okay. So, and this is great because this is the way transformers work. If we didn't have this principle right here, there would be no such thing as a transformer. And what does a transformer do for us? Yeah. Now, of course, so we have a bunch of coils of wire. So one thing, it depends on how many loops you put. And they have to be wound in the same direction, right? So what happens is when you put a loop of wire, the magnetic fields do what? They combine. They add. Everybody understand that? And then what we do is we bring another loop over here, which so we call this the primary, and we shouldn't have to do this because all y'all have had motor controls, right? Now, what a transformer doesn't do is it doesn't change power. People don't understand that. Power consumed will always, and this is not exactly true, because if you had a 100% efficient system, power consumed would be equal to power produced. That means I go up here and I turn on a 100-watt light bulb, and whatever power plant I'm getting power from is going to have to provide me 100 watts of power. Y'all understand that? Of course, that's not exactly true. It's not the power plant's going to have to provide a little more because there's no such thing as something that is 100% efficient. So basically, power used is going to be less than power produced, but that's because of the efficiency of the system, right? You understand that? But for all practical purposes, these transformers are extremely efficient now. They're over 95% efficient. So we assume that power in equals power out. That's the power factor. Yeah. Which we're not going to get to it much in class. We did it in motor control. So the way these things work is they work by induction. So what happens when the magnetic field comes out, it cuts those, which takes that energy from the magnetic field and produces a current. Now notice it's coming out of this one, it's going into that one. So if this took a voltage like that, then the voltage over here would be just opposite, right? You understand that? Everybody okay? But so what two things did I have to have? Number one, I had to have a what? I have to have a magnetic field. What's the second thing I had to have? I had to have conductors. So I had to have one conductor. And this is not true. I could use a magnet, and I can move a wire through a magnet. In fact, in motor controls, I showed y'all that big magnet, and I moved a wire through it, and I made an EMF, right? And what's the third thing? What do we need? Number three, huh? Yeah, we need motion. So that either means the magnetic field has got to move, right? You understand, or the conductor's got to move through the field. What's nice about AC is AC generates a moving magnetic field. So this is why transformers work. So I could put 120 volts DC on that thing and I'd burn up my transformer because all it would see is the resistance of the wire, right? You understand? It wouldn't pass anything from primary to secondary. So that means I can come over here and have a magnetic field, and if I come over here and put a little current transformer there, it's going to induce a voltage depending on the strength of the field, right? You understand that? So we have clamp-on ammeters, but a clamp-on ammeter only works with AC unless it has a Hall effect sensor in there. If it's got a Hall effect sensor on there, it means the clamp-on ammeter can also measure what? DC. Because that's what a Hall effect does. It measures a magnetic field. It don't have to be an AC field. It measures a magnetic field. So, but those clamp-on ammeters, if they can measure DC amp using the clamp-on, they're pretty expensive because now it's got more electronics in it, right? Oops, wrong slideshow. Where's my other slideshow at? Oh, that's not it. I must have closed it out completely, guys. And by the way, this slideshow is not completely on the. I'll have to put it back up there because there's some things I added to it. So we'll have to look at Hall effects. Hall effects are easy. Capacitive and inductive. So this will be about the only thing we talk about in this class because I think these are all the sensors that's on these lines. So we have limit switches, we have photo optics, we have Hall effect, and we have photoelectric, right? I forget one. And we have capacitive and inductive. Capacitive and inductive sensors have no moving parts, no physical contact with the items being sensed. They can be operated in really dirty environments. Capacitive sensors will detect both gases, solids, and liquids. So you can be designed to detect almost anything. So a capacitive sensor would detect glass if we wanted to. An inductive sensor only detects what? Metals. You understand that? So capacitive sensors can detect almost anything, the presence of almost anything. Inductive sensors can only detect metals. So over there on the manufacturing line, on the Festa, on the Amatro line, we have both metal blocks, right, or bodies, and we have plastic bodies. The line puts them together depending on what they are. How does it know? Well, it can use a what? It can use an inductive sensor. Now it can tell if it's what? Metal. If it's not metal, it's got to be what? Plastic. So it uses a diffuse sensor, it uses a reflective sensor to see if something's there. Then it uses that inductive sensor to see if something's there and it's not metal, it's got to be what? Plastic. If something's there and it is metal, then it's got to be the metal. So pretty easy using these things, we can detect different types of devices. So these are capacitive, and I left something out, by the way. Undoubtedly, I didn't put up my newest version. We have two types, depending on how we mount them. Let me go over here to these. This is an inductive, and notice they're very similar. They look a lot alike. So it's up to you to know what type it is. Notice some of them have the sensor protruding out. Some of them is actually flush mounted. The flush mounted, these are called shielded. The ones that where the sensor actually sticks out on the edge, these are called unshielded. What would you think the advantage of one over the other would be? Well, one of them has a greater range. Which one do you think would have the greater range? Huh? The unshielded has a greater range because more of its sensing element is outside that metal, right? You understand that? What would advantage would the shielded have? Well, these guys are flush mounted. So that means if I'm gonna have this thing slide over the top of that, I'm gonna put it on a belt or a chain or something, and if we want it to slide across the top, then of course we'll use a shielded. It's going to have to be a lot closer to the object that it's detecting. So when we get to inductive and capacitive sensors, we can get them shielded or we can get them unshielded. But what happens if we was to look at the sensing bubble? So one of them has more of the sensing element exposed. So here we got the unshielded, and then it's got thread. So this thing here is going to develop an envelope like that because it's got more of the sensing element exposed. A shielded, it's flush mounted, so it's going to develop something that looks like this. So basically, it's just going to get the crown because it's not going to come out the sides anymore because it's shielded, right? You understand that? So the shielded has less of a sensing range. But these guys are going to be right up against what we're trying to sense, right? You don't understand. So I've got a slide out there, and the unshielded is going to slide across the top of that thing, right? You understand? And we don't want it to pick up all this other garbage around here. All we want to do is pick up something when it slides across the top. So that's where we use a what? A shielded. An unshielded means I want to pick out something over a greater range, right? You understand that? Which causes a problem sometimes. So when we get these inductive sensors and these capacitive sensors, that's one of the things you have to specify is it is going to be what? Shielded or unshielded. So shielded means we actually shield or keep some of the output inside the sensor. It can't get out, right? You understand? So what does capacitive sensors do? They can sense almost anything, right? You understand? And then what? Go ahead. Yes, they can sense metal. They can sense metal. They can sense plastics. They can sense liquids. They can sense just about anything. The problem is that you're going to get a different feedback depending on what you go into, right? You understand? So that means the range varies depending on the material that you're sensing. And this is also basically true with inductive sensors. Inductive sensors, the range varies depending on the type of metal you're sensing. So a lot of people have metal detectors. Basically, they can come in and they can do all that. A lot of times you can tell you what type of metal it is because it knows by how much energy that device absorbs, right? You understand? So yeah, I've seen metal detectors that say, okay, there's a dime down there because it's made out of a different metal than a nickel, right? You understand that? Yeah, metal detectors, those metal detectors handheld, you can get some really expensive ones too. And they'll show you how deep it is. It's just pretty neat to see how far it's deep. If you go to the beach and you get up real early, like 6 o'clock or something like that, there's usually always somebody out there going around the beach with one of those things. So, capacitive sensors. So if I need to sense a lot of different things, we'll use a what? A capacitive sensor. If I want to sense nothing but metals, we'll use what? Inductive sensor. This is the formula, by the way. So what we do is we get into a field that's an electrostatic field that's generated, and what determines how much we get would be the type of material that separates the insulator that separates what we call the plate. That's basically what we're doing. We're changing this insulation or the dielectric stuff. But we don't really need to know that. We just need to know that they do what? It depends on the metal, how much they can actually sense. Ultrasonics. How does ultrasonics work? And this is the very last sensor we'll talk about in this class. How does ultrasonics work? How do they work? Yeah, what it does is it shoots out ultrasound, which is high frequency. And when it hits something, it does what? Bounce back. And that's ultrasonics. Sonar. Well, no, it's the same. It's the same. It is the same. Ultrasonics is usually a little faster than a sonar. But it all depends on the energy. Normally, you can tell how much energy the sensor is by the size of the sensor. So normally, the bigger the sensor, the more energy it has, and the further it's going to be able to detect. The smaller they are, usually the less energy it has, and the less. That's just a rule of thumb. Now, the only other sensor we have and it's not being used, and there's a lot of sensors on the Amoco line that are not being used, but they're on there, and it would be up to the user to figure out how to use them. We got a camera in there that we're going to figure out how to use in the lab right here. not as easy to use as you think they are because you have to program them to look what you're looking for. Ultrasonics, pretty straightforward. Sends out a sound wave and then measures the amount of time for it to reflect back. So it knows the frequency and know how fast it travels. So very easy to be able to determine distance. So we use ultrasonic sensors for a lot of things. The main thing is to detect distance. So we can use them to detect presence, right? Just set the sensitivity on the way we want it. So what we do on the Amatrol line, it's got two. It's got a deadband in there. So what we do is we set an upper limit and a lower limit. So what it does is it goes back and it measures those cases to see if they're either too big or what, too small. And we'll show y'all how to calibrate that. That's one of the things y'all have to do. And this class is calibrate that thing. And it's not that hard. Well, we can use them to sense speed. We can use them because they call it the Doppler so radar detectors. That's basically using the same thing, right? It's shooting out a beam of sound, and it reflects back, and they know the speed. So it hits this one, right? You understand? Then they get a start spot, and it shoots out another one, and you bounce back from right here. It calculates your speed between the distance between the two reflections. And putting aluminum foil in your hubcaps don't make any difference. Of course, a lot of them are actually using radar. A lot of them are using ultrasound themselves. And some of them are using photoelectric too. Yeah, the problem is that they had these radar detectors that picked up those energy, and you could pick up the energy before you got up to the detection range. And everybody had one. And so what they started doing, they started going to diffuse reflective, so they'd shoot the light beam out, the laser beam out, and then they'd time that how fast it reflects by. And then they got the detectors try to do something about that, but if they shoot that thing into the bumper of your car and it's a laser beam, odds are, well, you're not going to be able to pick it up. So anybody got radar detectors in the car anymore? Yeah, just about. Because there are very, very few of them use radar anymore. Not unless you get into some old ones. So ultrasonics, we can use it to sense distance. We can use it to sense movement. We can use it to sense solid or liquid, speed, direction. So these guys here are used a lot. The big tank farms down there off Interstate 65, those gasoline farm. That sucker's not oil. They still white in those ones. Gasoline. So that's the way they measure the height. They use an ultrasonic sensor that's in the top, and they reflect it off the gasoline, and they know how full those things are. Huh? I don't know. So these are ultrasonics. Of course, this is, I had to use a few of these when I was in the hospital, looking around. You can use it on Arduino. This is just an ultrasonic, or one of our robots use that exact sensor. By the way, we have pressure switches on both the lines because we're generating a vacuum, and we need to know if the vacuum is being generated or not. So a pressure switch is pretty straightforward. It just measures the pressure of the fluid. Our pressure switches are measuring the pressure of the air. So we're not actually measuring the vacuum. It runs both of our lines use what they call a Ventura vacuum generator. So what they do is they bring it up through big sites, and then they narrow it down, and when it speeds up to go through there, it generates a vacuum. And so what they're doing is they're measuring the pressure of the. Some of them, we don't have a vacuum pump on either line, so they have a Ventura vacuum generators. And we'll go see that in a minute. These are just different rays. And of course, we have a RFID system on there that we don't know how to use yet. So these are radio frequency identification. These are pretty neat. You run into these all the time now in department stores. What's nice about we have most of your RFID tags are passive. So what do we need to induce a voltage? Well, we need a magnetic field, right? You understand? And we need a frequency and we need a conductor. So that's all a passive tag is. So a passive tag don't have any batteries or anything in it. It's got a little electronic circuit in there, and when you move through that field, the transmitter, it powers up the RFID tag. And then once it powers up, then it transmits that information that says, okay, somebody's trying to steal me because the tag's still on there, right? They can put all types of information on those little passive circuits too. So we have people now that you can walk through a thing when you go to work. You walk through there, you got your ID bag, and they know what, they know you're here. You don't have to punch in or anything, and that's what Thomas is trying to tell y'all. He works for Revere Controls, so they use a little RFID tag reader for their ID cards. So they don't have to swipe or anything. I wish we had something like that for attendance. So come in. We talked about it too. It's on security that was talking about. Of course, it was the system was so expensive that it was prohibitive, but they was going to lock all the doors to keep people that wasn't supposed to be in the school, and you'd have to do what? You'd have to come in and swipe your card, and it would unlock the door for you, and it also would record it. Yeah, but it's not a. Yeah, we thought about doing that. So right now, I couldn't even. Right now, this right here, don't know. I know we have one, but it's not being used now. It would be something that we have to figure out to use. But we'll show you where it's at, and then we'll show you some of the symbols that have the RFID tags on there. Okay. So what do we need to look at? And this is it for sensors, guys. Y'all go ahead and take a 10-minute break.